So, what we show to you today is what's called a Jupyter notebook. Jupyter notebooks are similar to a data recipe, like a workflow that's written up in text, in graphics. But the difference between a PDF workflow description and a notebook is that the notebook contains, as you will see in this, if you scroll through this notebook, it contains executable code. In this case, this is programming code in language Python. If you're not familiar with Python, that is fine. You don't need to program today. We'll just run the code. So what it allows you to do is it doesn't just write up the workflow, but it actually allows you to execute and run the workflow as you read through the document. Notebooks have, in essence, two different, it's built out of individual cells. If you look at my screen and if I click into this cell, you see that there's a frame around that cell. This particular cell contains text and graphics. These kinds of cells, they are labeled as so-called markdown cells. You can see that up here on the top menu bar. There's a drop-down menu which, where you can pick what kind of cell this is. So this is labeled as a markdown cell, and markdown cells are used to, provide text and instructions, graphics, equations, etc. In addition to these markdown cells, which you see here when we scroll through the notebook, there are interspersed these so-called code cells. Again, if you click in this cell and you look into this drop-down menu, you see that this one's now labeled as code. And so these are the cells that we can run to exercise code and actually do the work that's described in the notebook. So, so this notebook, Africa presented early on a workflow to do change detection using SAR image time series. So one thing that SAR is really good at is looking for changes on the surface. That Vanessa presented at early on. If a radar comes over the same area, say 12 days later after first acquisition, and takes another image, the image theoretically looks identical because we are taking the image from the same location and we are transmitting actively signals to the ground. So if the surface itself has not changed, the image will look the same. And so differences between images all have physical meaning that relate to changes in moisture, either vegetation moisture or soil moisture, or changes to the structures such as deforestation, vegetation growth, etc. So it's a really good tool to identify places where things have changed. And so this notebook encodes a workflow that was presented in the notebook, the so-called change point change detection approach. And we use it specifically for looking at a deforestation site in South America, in Madre de Dios in Peru. So in the beginning, it tells you a little bit what the notebook is doing. So this is this change point detection workflow on a SAR data stack. And the site here it's Sentinel-1 data. We have 21 images of C-band Sentinel-1 data sets. They're all provided as RTC images. So all of those are already created as RTC images. And the site is Madre de Dios. There's some more information about, if you wanted to download this notebook, etc., you can read through this information on how to access the notebook. And so now we are actually going to step through the workflow step. Oh, sorry, my notebook fell asleep on me. And so the first things we do when we go through any notebook is, and if you're familiar with programming, in programming, the first thing you need to do is you need to load all the libraries that you will use. And so there are a few libraries that we're using here. There's a library called Pandas, which allows us to work with data structures that includes different dates and different locations. We will use a library, a programming library that's called gdal, which allows us to work with geospatial information, GIS information, coordinates, etc. We'll use a library called NumPy, which allows us to do mathematics and mathematical operations. And we'll use a library called matplotlib. All of these are Python libraries. Matplotlib is a plotting library. It allows us to visualize data. So if you're familiar with Python, you know these libraries. If you're not familiar with Python, you probably don't, but it's okay. I'm just telling you that these are the libraries we're using. So as you scroll further down, you encounter the first code cell. And the way you actually run the code in this code cell is you click into the cell, as I have done now. So you should now see a frame around that cell. And then there is up in the main menu bar, there is a button that's called Run. If you all see that button, please then click this button. And what happens is you see a little star in this bracket over here when the cell is being executed and run. And once the code has run entirely, this star is being replaced by a number. And so here we have the number 1 because it's the first cell that we run in this notebook. So can you give me a thumbs up if you were able to run this code cell successfully? Okay, excellent. So now, that we've loaded the libraries, now we are ready to actually do the work that we want to do in this notebook. And so the first thing is we load our data sets that we want to analyze. And so again, these are 21 images. It's in this case VH polarized data from the Sentinel-1 mission over the Madre de Dios site in Peru. On the right-hand side here, you see a graphic, figure that shows a little bit where this site is located. You probably all know where this site is. The data sets that we are using, these are Sentinel-1 data, and they were created as RTCs by ASF using the custom processing ASF RTC processing workflow. So this site is very dynamic. There's a lot of deforestation going on. And so we will be looking at that deforestation. So in order to load the data sets, you see there is one code cell that you can run real quick. So please run this little code cell here. It is creating a little function that we will be using later on. So this function says get TIFF paths, and it's one that we will use to find all the GeoTIFF data that we will be using and load those data sets in. Okay, so now we are ready to read the data stack in. So if you are down here, please feel free to exercise these coming code cells all the way down to to the next section. So there's 1, 2, 3, 4 code cells that you can all run. The first code cell that I'm running now is retrieving the data. This is a prepared data stack that we parked in a cloud-based storage space. So these data sets are being loaded out of a storage bucket in the Amazon Web Services cloud. What this code cell is doing, it is retrieving the zip file from the cloud storage, and then is extracting, unzipping all the files so that we can work with the data sets. And what you see here is we do have 21 different TIFFs for a time frame somewhere between 2017 and 2018. I'm going to walk through these next 3 code cells also. And so these code cells then retrieve all the VH images. We are working here only with the VH data sets, and tell us a little bit about the corner coordinates of the area that we're looking at. So these are UTM coordinates, and it also tells you about the UTM zone. And again, if you hopefully made it to this location and you get the output that I get, again, give me a thumbs up. Or if you have any issues, let me know. Okay, see some thumbs up. Excellent. So now we have loaded 21 images. These images are all stacked. They have the same extent. and we can analyze them through time. So, so before we can work with our data sets, we have to stack all of the 21 images up. We do that using a programming construct that's called Virtual Raster Tables, a very useful approach. It basically writes a little text file that in the beginning gives the geospatial information. So it describes the corner coordinates and the resolution and the coordinate system, and then just provides links to all of the layers that are included in this data stack. So if you execute this code cell, it is building this virtual raster table and is creating this text file. And now we can relate all images to each other in a time series sense.
Hi, Franz, sorry, quick interruption and a question. If you can expand more on where all this data is running. Because we are saying you're downloading, you're creating the virtual rasters.
Yeah. So where the notebook is running, basically?
Mm-hmm.
Okay, so this notebook, yes, I didn't say that. It is running in a online service that's called Binder. And Binder is a service that is being provided by an online data provider. It gives you a temporary workspace in the cloud and allows you to, it gives you a total of, if you look at the top right, it allows you a total of 2 gigabytes of memory. And within that memory constraint, you can execute workflows in this cloud space for free. So when you clicked on a link, it built for you a Linux machine in the cloud, and we're using this machine right now. This is available for you temporarily. You saw maybe earlier on that my notebook timed out. So I think if you don't touch the notebook for 5 to 10 minutes, it times out and needs to be restarted. And so it's perfect for rolling out workflows like this. You can then exercise the workflows to understand what is going on in the notebook with a prepared data stack without, without the requirement of installing anything on your local machine, or without the requirement of registering for any online service other than Binder. It's a very easy way of making these workflows available to you. I hope this answered the question you had.
Yes, thank you.
Okay, so now let's work with the data set. So what we initially do here in these first code cells is we now get all the data in an image stack sense. This is this code cell here. We then use some functions. This is a so-called pandas function to extract all of the time and date indices from the data, from the geotiff information. So this is the next code cell. And then the third one just plots the time series. It tells us how many bands we have. So we have 21 image bands, and it gives you an idea of what the time span is. So the very first image is from 2016, February 2016. The last image is from 2018, in this case, July of 2018. And in between, we have a data set, at least in the later part of this time series, every 12 days. It shows you all the dates. The way it's shown is sort of the American way with year, month, and day. So this is an easy one, but if we look at this one, this is the 1st of May of 2017. Okay. Now we can look into our data stack. So we can load the full data stack into a variable. So all of our data is now contained in the variable image. And then we can query information from that image. We can, again, look at how many bands do we have. We have 21 bands. Each little chip window or image that we're looking at has about 1,000 by 1,000 pixels. So at a 30-meter resolution, that's about 30 by 30 kilometers on the ground. We then create mask out some pixels. There are some 0 pixels or not a number pixels contained in that stack. Those we remove because we don't want them to bias statistics that we calculate. Okay. So now we can do this cumulative sums change detection approach that Africa presented in the slides. So first we transform our data set into the decimal space so that the mathematics get a little bit easier and the data look a little more Gaussian in their statistics. And then we are visualizing a data set. So we transformed everything into dB space, and now we are visualizing an image. The image I'm visualizing here is band number 0, which is the first image in the data stack. And this is what it looks like. So what are these light areas, the lighter colored areas in the image, you think? So you see that there are some places that are very light colored, other places that are very dark, and also places here that are very dark. What is the light colored stuff? Do you have any thoughts? You can type it in the chat if you want. What kind of surface is this? Vegetation, Diana, yeah, that's correct. This is forested terrain. Forest always has sort of these lighter colored gray values. The more biomass there is, the more structure the forest has, the brighter the forest gets. And so this here is rainforest, so it's a very deep, layered, structured forest, which usually shows up in these lighter gray tones. In contrast, so up here, you know what this is. This is a river. Rivers often show up very dark. You get specular reflection on the surface, so rivers are often very dark. And then what are these features here, these elongated features in the rainforest? So do you think this is, you know, what happened here? Floods? So you are partially right. So both of you are right, Mario and Fabiola. This is deforested terrain. So here the rainforest was cut down. The reason why it was cut down is predominantly gold mining in this area. The reason why this is so black, though, is this is a very low-lying terrain, and in the places where the rainforest was cut down, there's a lot of water on the surface. You have very high soil moisture or shallow water puddles on the surface. So both, you know, water and deforestation is correct. If you want, you can change up here the band number to something larger. Let's say we look at now band 15. You can change this up here to from 0 to 15, and then you can rerun this cell, and it will visualize a different image. And you see that it looks a little bit different. If you look at the extent or length of this dark feature, it's a little bit longer now. And if I go a little bit further to maybe band 20, you may see that, you know, the extent of the different surfaces here is changing. Okay. So now for the change detection, if you remember the workflow a little bit, the way the change detection works is we first calculate the mean of the area over time. So we take our 21 images, and for every pixel, we calculate the mean value across time. So this is what happens in this first step. We calculate the mean value and visualize it. So this is the temporal mean over time. You see that there are some areas that are fairly dark. Then there are these strange areas sticking out here that are darker, but not quite as dark. So here the multi-temporal mean is not quite as low, but it's lower than the temporal mean for the forest. Okay, so this is the first step. We calculate the mean. In a second step, for change detection, we now calculate the difference for every time step and every pixel to the mean. So we calculate how much a specific time step and a pixel in that time step deviates from the mean. So we calculate the residual. This is step number 2. So what we did here is we calculate the residuals by, for every time step, subtracting the mean value, the temporal mean from that time step. Louise, so the last data set we have here is from 2018, but what one does see in the time series is that the amount of, or the speed of deforestation has already started to slow down in 2018 because of that change of the rules that were implemented by the government. I haven't looked at data sets more recently. I know maybe somebody from SERVIR has, about whether the activity entirely stopped, or maybe whether there was even some regrowth. Not sure if anybody knows on the call. So what you see here, this is, so here we take band number 0, so that's the very first image in the time series, and we are visualizing the residual. So this is the original image minus the mean value. And so what you see here, for instance, in this bottom right corner in the southeast of this area, you see that there is a strong blue signature. So blue signature means that the residual is positive. What do you think this could indicate? If you have a residual, so original image minus mean value that is positive, what do you think this indicates? So it means in some way that these pixels were brighter in the time step 1 than they were on average in the time series. So it was brighter early on, and then later on it turned darker. And what could that mean? What could lead to these pixels getting darker over time? So at the very first time step, these pixels were bright. In this case, it's because there was, in the first time step, there was forest in these pixels. Later on, we cut that forest down, which means that the mean value or the brightness got lower. And so on average, these pixels then are darker than they were originally. And so we get these positive residuals. And we get them in many places where there is, there was expansion of deforestation over time. Again, for fun, you can change what you're visualizing here. So now let's look at something much later in the time series. I'm looking at band 15. And if we look at this residual, you see now that the residual in this area is now negative. And so now we are at a time step where the forest was already cut down. And the pixels are now darker in this place than on average. So all the places where these values are much different from 0, these are good places where things have changed, where likely there was change over time. Other places where you see lots of change is along the rivers. This is because rivers are dynamic. There's always, rivers are locating and relocating. There may be changes in water level and so on. So there's always change along rivers. Okay. So now that we have the residuals, if you remember the workflow, we can calculate the so-called cumulative sum. So the cumulative sum, in places where the cumulative sum is large, it indicates that in these places there was change and there was significant change. So the larger this change magnitude, the cumulative sum, which is this one on the right, the more likely it is that there was significant change in this region. You see there's a lot of places out here that are light colored, either light or slightly reddish colored. Those are places where there was not a lot of change in this time series. And there are other places that are blue, where there was significant change over time. So there are the deforestation sites. There are also places within the previously cut down forest where there was change. This could indicate, for instance, that maybe there's regrowth of vegetation in this previously cut down forest. It may also mean that if there was flooding underneath this forest, that the water surface has changed over time. But again, you see the deforestation sites and you see the rivers where you see change. So there's lots of pixels that appear like they could have changed, but we are not sure which one of them really has changed. So we want to make sure that we pick the pixels out of all of those that are the most likely candidates for change. So the way we do this, first of all, initially is we say, okay, if your change magnitude is lower than a certain value, we assume that you have not changed. And so this is what this step does. It first calculates a histogram of all the change magnitudes. So you see that most pixels have small change. So, you know, on the x-axis is the strength of the change. And you see that a lot of pixels have a very small amount of change. And there's a small amount of pixels that has very large change. So one way how we can select, initially select change candidates is we can say, we think that not more than, say, 15% of all pixels in that scene should have changed. So on average, most of the planet is reasonably stable over time, and deforestation is usually only at a subset of all pixels that we look at. So in this case, what we do is we assume that at maximum, we think only 15% of the pixels should have changed. So we set a threshold here. We only picked the 15% of pixels with the strongest change magnitude. And these are these candidates. These are the pixels that we selected. So black now are all the pixels that are change candidates based on their change magnitudes. There is a good likelihood that they may have changed. And all the white pixels are the ones where we think no change has happened. So, you know, in some ways we could stop here now. So these are pixels that, you know, look like they may have changed. But we want to know more. We want to know, okay, out of all these candidates, which ones are true change pixels and which ones, you know, are not really true change pixels. It may be that the change magnitude we see, maybe that was just created by coincidence. So we want to find out, separate the pixels where the change magnitude only was created by coincidence from those pixels where there was truly a change that happened. And so we do that in a last step that's called bootstrapping. So what we do here is we take the time series for every pixel and we scramble it. So we switch out time steps randomly and then rerun the process and recalculate the change magnitudes. So what we are trying to find out here is the overall change magnitude we got in our original data. Can that be created even if we scramble the time steps? If the answer to this is yes, then it means that maybe that's not really a change point. Maybe it was just you know, statistical randomness that created that change magnitudes. But if only the original time series creates that large change magnitude, then that is a good indication that it's a true change. So it's a little bit of a complicated process, but if you execute these code cells, first, you know, we select the pixels for which we want to do the bootstrapping. These are the ones that are shown in color. And then we run that bootstrapping. And so it runs through 100 iterations. So it changes the order of images 100 times, recalculates the change magnitude, and compares it to the original change magnitude. And in the end, what we will do is we count the number of times where the random change magnitude is larger than the original one. And if that percentage is large, then this pixel is not really true change. If only the original time series creates that large change magnitude, then we keep that pixel and accept that pixel as true change. So that's basically a last step to verify which ones of our pixels are good and which ones are not useful and are not truly change. So this takes a bit. You see here now it's done 30% of the runs. And once we are through all the runs, we can visualize the result and then get our final change detection map.
So we see like 100 runs right now for the Bootstrap. Would it be possible to have fewer? Would be as good, or if we have more, will be better?
Yeah, so you have to have enough runs to create enough samples so you can make a solid statistical decision. So in the end, we'll use all of the repeated runs to make a decision based on statistics. So if my change magnitude was in the top 10%, we may accept it. And so you may want to run enough iterations so that you can create solid statistics. So that's at the minimum.
Sure.
There's always a rule that if you wanted to calculate a robust mean, you should at least have 30 samples and so on. So 100 is a good number. Actually, you probably, if you want to be more accurate and more certain about your decision, you may want to do more than 100. But yeah, so the more you do, the more statistically certain you are.
Thank you. Yeah. So at minimum 30, minimum
At
to be a
minimum 30.
statistical significance.
Yeah.
Yeah. And just because this process, if we want to run it for a larger area, longer time series, this is the process that takes most of the memory, and it can be very
Yeah, so this is the slowest of all steps.
Yeah.
If you have a larger site, you will need, first of all, you will need a lot of memory, but it's going to run a little bit. You can, walk away and get a cup of coffee or a cup of tea and come back later. So now we've run our change point, our analysis, and we get some output. We are calculating two different statistics here. I'm not going to go great into detail, but the confidence level, this describes how many of my 100 runs created a change magnitude smaller than my original run. So areas that are shown in yellow, those are great because it means like only the original set of data sets created a change magnitude that large. All other scrambled data sets had lower change magnitude. So those yellow ones are really good candidates for true change points. As the values fall to like 50% and lower, we're not so sure anymore whether that's a real point, a real change point. We also calculate significance. Significance calculates the ratio between the original change magnitude and the random change magnitudes. So the larger the significance, again, the more likely it is that this is a true change point. There's no hard and fast theory behind which of those indicators is better. So you could just use the confidence level. You could only use the significance. What we do here is we actually multiply those two. So we use significance and confidence together, and we get sort of this combined indicator over here. So now is the most difficult step, is once we calculated all of these numbers, now we have to make a decision. We have to set some sort of a threshold and say like, okay, if this indicator is larger than a certain value, we accept these pixels. If it's lower, we won't accept these pixels. For this multiplied data set, it's a little bit, your expertise to come up with a value that you like. Often what you probably would do is you would set an initial threshold, calculate a result, look at it, maybe, go back and change that threshold a little bit. So that's a little bit harder to do what this, final threshold would be. I'm setting here a threshold of 0.37. which would give me this kind of map where in blue, or in this kind of bluish color, I'm showing the pixels that I accept as true change pixels, and in this pink color are pixels that in this case I would reject based on my indicators. So I'm accepting most of these pixels over here, some of these pixels down here, and so on. So now these, I'm in some ways done. These blue pixels are now my change points that I selected, but we can actually at the very end do more. Once we detected change in a pixel, we can also pinpoint when that change has happened. That was also in the slides that Africa, in the slide that Africa presented. For each of these change points, we can count or calculate the date at which the main change happened. This is what these last code cells are doing. And so if you made it all the way to the end, you should get a map like this. And so what's shown here in color is the date at which the main change happened. So the dark blue is a bit confusing because it basically, these are all the pixels that we rejected. So the dark blue are pixels that haven't changed. And all the other ones are indicated by the date of change. And maybe it's best to look at this piece down here. You see that the pixels closest to the west, they changed first, maybe around May of 2017. So this part of the forest was cut down in May of 2017. Then it changes from blue to green. So these green colors are between July of 2017 and maybe October of 2017. So this piece got deforested in the second half of 2017. And then it goes into these reddish colors, which indicate deforestation later in 2018. So this makes a lot of sense physically, and it shows you how over time the deforestation has progressed. And you could use that to understand what is the rate of progression. So when progressed deforestation the fastest, and when did deforestation slow down? So to answer, was an earlier question on, whether the rate of deforestation has changed. So this data already indicates that the in sort of late 2017, early 2018, it seems like the deforestation has slowed down. If you have a longer time series, you could analyze that longer over time. So this is just to give you an idea of how these data sets can be processed in sort of an example workflow of as to how these time series can be analyzed. So I hope that made somewhat sense and gave you a little bit of an idea.